Okay, so we're working on a center of mass problem, and we have already computed the mass of the solid that we're looking for the center of mass for. So what's left to do is compute the moments relative to each, or the moments of the solid about each coordinate plane. So what I'm going to do is just find one of them. I'm going to find M, Y, Z, and remember that's the moment about the YZ plane. This is defined to be the triple integral over E of x times our density function, which is just 4. Notice that because we're integrating over the same solid that we did over here, the limits on the triple integral are going to look essentially identical. So it's still going to be the integral from -1 to 1, 0 to 1 minus y squared, and 0 to 1 minus z. It's just that the function that we're integrating looks like not 4, but 4x dx dz dy. Okay, so I just go through the steps of integrating this. This, if I integrated with respect to x first, is going to look like this, 2x squared from 0 to 1 minus z dz dy. We plug in 1 minus z and 0, but 0 doesn't really do anything. In fact, I'm also going to pull this 2 out of the integral just to keep things a little simpler. -1 to 1, integral from 0 to 1 minus y squared. And then I'm squaring this, so that's going to be 1 minus 2z plus z squared dz dy. Okay? Excuse me. So, the next step would be to integrate with respect to z. So we do that. 2 times the integral from -1 to 1 of, this will become z minus z squared plus z cubed over 3 from 0 to 1 minus y squared dy. Okay? This integral, once I plug in the 1 minus y, notice again I'm using a 0 here, which is convenient because I don't really need to do anything with it. I can just plug in the 1 minus y. This will get messy because the integral, or the algebra, is kind of cumbersome. So what I'm going to do, as I've been doing, is just skip straight ahead to the simplified version of this. I'm going to get 2 times the integral from -1 to 1 of what's going to look like 1/3 minus y to the 6th over 3 dy. I'm going to do a couple of things here. First of all, I'm going to pull a 1/3 out to simplify, and then I'm going to use the fact that this is also an even function, just like what we had over here, to change the limits of integration from 0 to 1, and then double that integral. So pulling the 1/3 out gives me 2/3 here, doubling it gives me 4/3, and I get to double it because I'm changing the limits here. I have 1 minus y to the 6th dy. Okay, this becomes 4/3 y minus y to the 7th over 7 from 0 to 1, which this will become 1 minus 1/7 or 6/7 times 4/3. After simplifying, I should get 8/7 as a result. Okay, now that's the moment with respect to, or the moment about the xy plane. So that's up here. We did all that work. This combined with the mass here can give me the x bar that I need for my center of mass. So again, I take the moment that we just found, 8/7, divide that by our mass, 16/5. Do a little simplifying there. What we should end up with is 5/14. Okay? Now, I want to point out that this will have to be done a couple more times, one for the moment with respect to my x, or the moment about my xz axis, and one for the moment about my xy axis. Notice the only difference in each one of those integrals is the variable that shows up here. I'll use either a y or a z in the other two integrals. And the integration itself, it's not going to be identical to this, but it's going to be just about as difficult as this was. So it's not really worth going through those two integrals. Again, I'm going to jump straight to the answers just to save some time, but you've now seen what that process looks like. Y bar, remember this is going to be mxz over our mass. Now mxz, it turns out, is going to be 0, so 0 over the mass will also be 0. Z bar is going to be mxy over m, and if we were to work out mxy, we end up with 32/35. Divide that by the mass, which was 16/5. Simplify everything down. This one comes out to 2/7. So together, these make up the coordinates of our center of mass, which I'm going to write over here. 5/14, 0, 2/7. And that should wrap that one up.